Hi guys, this is Ajit. So we are going to be solving the today's LeetCode question, which is cherry pick 2. So we are given a question we are given a matrix which is grid, and grid of ij represent number of cherries which are present in that particular cell, in the particular cell of ij. Now we are given that there are two robots which is at the top left corner, and then the other position is top right corner, and we need to calculate the maximum number of cherries collection using both the robots by following rules. So we need to calculate number of cherries we can collect via these two robots, and we are also given the positions of these two robots, which is like 0 0 and then 0 comma columns minus 1. One is at the left corner and one is at the top right corner. And for let's say we have a robot, and we need to move the robot to next cell. Then there can be three transitions which we can make. Like, it will move to next row for sure, but the column might be decreased and the column remains same, or column will be incremented. So these are the three cells which we can move from ij to other cells. And when any robot passes through the cells, it picks up all the cherries. Suppose let's say we move one robot to another cell, then whatever the number of cherries which are present at that particular place, it will pick up all the cherries. And then when both the robots stay in the same cell, only one takes the cherries. Suppose let's say here there is robot 1 and then here there is robot 2. Suppose if we move robot 1 to 5 and then robot 2 to 5, then only one of them will pick up. Suppose let's say this column is remains same, then we can say that only one time we need to consider the grid of ij, and then both robots cannot move outside of the grid. Suppose let's say you are here, you cannot move outside of this particular grid, and both robots should reach the bottom of the row in the grid. That means here we are given two robots and then it should reach the bottom at that particular time. What will be the maximum answer we can get? So this is the question. So let's say uh, let me explain what is the transitions we can make from each cell to another cell. Suppose let's say you are here in this particular cell, you can move here and then you can move here and then you can move here. Suppose let's say robot 2 is present here, then you can move here, you can move here, from here to here, and then from here to here. These are the three possibilities from one place to another place. So the row will always increase, it will become I plus 1, and then j will become minus 1, j minus 1, and then j might remain same, and then j can be incremented. So these are the three possibilities which we can make. Suppose let's say at particular position, so this is 0 and then this is still, let's take m, and then this is m minus 1. So these are the number of rows which we need to move on. Suppose let's say you make a transition from here. So what are the possibilities for robot 2? There will be three possibilities for robot 2, and then what about robot 1? For this also there will be three possibilities for the particular row. And then what about here? Here also remains same, it will be 3. The maximum it can go is 3. Here it is 4, but the maximum it can go, let's take it as 3. and then it will be like till m minus 1 as well. So if we calculate all possible cases, then it will be 3 3 ja 9, and then 9 power m. So this will be 9 power m, and then if we see the m number, it goes to 70. So it will be 9 power 70. So it will be 9 power 70. So we cannot calculate on that. Suppose it will be time limit exceeded if we calculate all these things. Suppose let's think like what are the different scenarios which we want to store. Yeah. Suppose let's say, yeah, uh, let's take one example, so that let's take this position, and then again take this position, and then for this particular case, this one, and then this one. So these are the two cases which we like. These are the two transitions which we made for robot 1 and then robot 2. Suppose let's think another way we can get here, like here one transition, and then from here to here, and then for this as well here, and then from here to here. So if we see, the answer for this transition might be different, but if we consider from here to all the way through last, from here to all the way through last, then we can say that the answer remains same for this particular case, from here to here, but this answer might be different. So whenever we are doing again and again computation, it doesn't mean like we need to do again and again, which the problem is already solved. Suppose if this particular answer we got, and then now again we are solving the same sub problem, then it doesn't make any sense. We can store the whatever the solution we had got previously, and then we can store it, and then we can return it back. So if we consider the state of particular robot, and then state at which it is present, so we can say for the particular robot I1, there can be row 1. Let's take it as row 1. For robot 1, the row will be row 1, and then column will be column 1, and then for robot 2, row will be row 2, and then for column will be column 2. So this is the particular state for two robots which are present at the grid, and then for this particular case we will get the answer, and then we can store it back. And one more thing, if we observe, the row will always remain same for both the robots. So you can take out one row and then take it as row common, like it will be same for both the robots, and then column might be different for both the robots. So you can store the state in like this: row, and then column 1, and then column 2. So if we consider this particular case, so then it will be columns, the maximum it can go is 70, and then here it is 70, and then here it is 70, so which is approximately less than 10%. So you can store this, and then you can calculate the answer, and then you can return. So yeah, this is the intuition. Like we'll take all the possible cases, and then we try to reduce the problem by removing whatever the duplication, and then we have a state by representing row and then column 2. So we can code this up. So we'll take dp int dp of 71 and then 71 and then 71, and then we'll take m and n, which represents the rows and columns, and then we'll assign m equal to grid dot size and n equal to grid of 0 dot size, and we are going for each loop, and then we'll assign the we'll assign for dp equal to -1, so that the problem will not, it represents the problem is not solved yet. And then here we are going to write the dp. It will be recursion by taking row as 0 and then column 1 as 0 and then column 2 will be column -1, and then we are going to pass the grid which represents all the cells which are present, and then we are going to write the recursion function which will take row and then column 1 and then column 2, and then it will take grid. And suppose, let's say, if the problem is already solved for this particular row and then particular column, then we are going to return the answer which we had got previously, column 1 and then column 2, and then again we'll take the current cell answer, current cherry, current cherries equal to 0, and then next cherries will be 0. So now current cherries we need to pick for this particular row and then column 2. Suppose, let's say, if column 1 not equal to column 2, then we need to pick for both the cells. So it will be current cherries will be grid of row and then column 1 plus grid of row and then column 2. Else we are going to say current cherries will be grid of, just only one will take because both are in the same column. And then one more thing we need to consider is, suppose, let's say, we had got here this particular cherries. Now we need to get all these cherries. So for all these cherries we need to find the maximum cherries. So we'll take all the possibilities. So for all the possibilities, let's take directions equal to 3 equal to -1, comma 0, comma 1. So this will give the transition. If it is -1, it will come like this. If it is 0, it will come like this, and then for +1 it will go like this. So these are the three transitions. And then one more thing we need to consider is, suppose let's say row double equal to m-1, then it is the last row itself. So there won't be any cherries which will be present outside of the grid, so we will not take that case. Now here we are going to consider all 9 cases, which will be I equal to 0, I less than 3, I plus plus, int j equal to 0, j less than 3, j plus plus. And then here we are going to consider next column 1, next column 2. So for next column 1, we'll consider next column 1 equal to column 1 plus direction of I, and then this should be in the boundary. That means it should be greater than or equal to 0, and then it should be less than n. So this should be the condition. Why? Because it should not go out of the grid. And then here again for column 2 we'll do the same thing again. Next column 2 will be column 2 plus direction of j, and it will be same if, what is it, next column 2 should be greater than or equal to 0, and next column 2 should be less than n. And then next cherries will get all the possible cherries. Out of that we'll pick the maximum. So next cherries equal to maximum of next cherries, and then we are going to call the recursion with row should be increased, so it should be row plus 1, and then column will be next column 1, next column 1, and then another next column will be next column 2, and then again we are going to pass the grid. So this is the transition we are making. We are taking one column by moving in one of the direction, and then for next column we are moving in another, like it can be 3 into 3 possibilities, 9 possibilities. Out of that, the row should be moved to next, and then next column will be moved to next column, and then next column will be moved to next column, and then we are taking the grid. And then at last we need to return, we need to store the answer whatever we had got, and then we are going to return the answer dp of row, and then column 1 and then column 2 should have current cherries plus next cherries as well. Yeah, let's see the code again. If there are any mistakes, m will have, okay, and then we are marking everything to -1, and then we are calling this function recursion 0 n-1, okay, and then grid. For this we had defined the dp and then m and n and then directions and then row column, and then if it is already solved, return it, and then current cherries will be like this. And if both columns are different, we are taking both the grids, both the cells answer cherries. And then if both columns are same, then we are going to consider only one. And then if this one, yeah, this is not equal, this should be not equal, row should not be equal to m minus 1, then only we are going to consider next cherries. So int equal to next column and then next column 2, and then we are moving through one of the direction, we'll get next column with the direction, and then next column should be in the boundary. And then for next column 2 we are going to consider three other cases, and then we are going to say this next column, it should be in the it should be in the boundary, and next cherries should be maximum, okay, and then row column, and then at last we are going to say current cherries and then next cherries. Yeah, let's try to run this. Yeah, let's submit this. Yeah, it's passed. Yeah, thanks for watching.